Hi, I'm Happy, or Erik Stenman, but most people call me Happy. I've been working with programming language implementations for many years. I've been working with Scala and Erlang, and for last year I've been working with smart contracts for Eternity. And today I'm going to talk about Sophia, the functional language for the Eternity blockchain. Before we dive into the Sophia language and some of the aspects of the language, we will talk a little bit about Eternity and the background for that. I will not talk so much about all the features of Eternity that we have, but just a little bit about the background as it affects the design of the language and the virtual machine, or at least Sophia. So the big motivation behind Eternity is to have a new blockchain design which is more efficient and has transparent governance and global scalability. So the transparent governance is not the subject of this talk at all, really, but the global scalability is not so much the goal of this talk either. That has more to do with how that we're using Bitcoin NG to scale the blockchain and state channels to take transactions off the blockchain. For the efficient part, we're trying to design an efficient language and virtual machine, but also by having many of the objects that you would find being used in, for example, Ethereum over and over again as quite heavy and expensive smart contracts. We've lifted them up to first-class objects in Eternity. So Eternity comes with oracles and names and state channels and contracts already implemented. Tokens and governance will come soon into the implementation. So for the contract and smart contract execution, we wanted it to be safe, efficient, and to scale, and to be cheap. We also wanted there to be a way to migrate from Ethereum to Eternity smart contracts. So for the last goal, we have implemented AVM, a virtual machine that runs Ethereum virtual machine contracts. To get cheap execution, we have a new language that it's called Varna, that should be cheap, and this can also be used for efficient and scalable execution of smart contracts. And for the first goal, to have safe contract, we have defined the language Sophia, which is a functional language. So why did we choose a functional language? So functional language has many benefits. One is that there's side effect free computations, so there will not be things happening behind your back when you're running a Sophia contract. You will see what is happening, and it's strongly tied so that you cannot mix up the way you're using functions and variables and values. They will all have types, and you should not be able to compile programs that uses these values in the wrong way. With a functional language, it should also be simpler to do proof of the language, something that we hope to take advantage of soon. And at least as I see it, with a functional language you get shorter and more readable code. Let's look at an example of that. Here we have a code in an imperative language and in a functional language, trying to sum the values between 1 and 100 and also storing them in an array. So actually I managed to make two mistakes, or actually three mistakes, when I wrote the imperative version of the program. So in the imperative version, we're using a for loop, counting from 1 to 99, that's 1 less than 100 for integers. And we're storing the value of the variable I inside the array values. Unfortunately, I managed to write a 1 here instead of an I, so this loop will never end. That's not really a bug that you get with any support from a functional language to get rid of, but just that the code that you're writing is a bit more wordy. It's easier to make simple mistakes like this in an imperative language. When we have initialized all the values in the array, we do another for loop going through the length of the array and summing up the values. And here I managed to start from 0 instead of 1. So what values 0 is undefined. Also I forgot to initialize sum to 0. So the thought was that this would actually sum up all the values in the array, but since the first value of sum and also the first value 0 are undefined, we don't really know what we will get out of this. In a functional style, we would just write let values and then get a list 1 to 99. So here we get very easy to see that we just get the values 1 to 99, no mistakes there. And a little bit more complex, but once you have learned it, very easy to see and read, is things like the fold function that takes an accumulator and a list of values in this case, and then applies this function that takes the argument x from the list of values and y from the accumulator, returns a new accumulator by summing x and y together. So here we declare an anonymous function, and then we send this function to the fold function and apply it to each value here, adding the values together, and we start from 0. So a very concise way of doing summing the values in the array. So even if I hadn't made the mistakes in this code, the code here is a bit more verbose and harder to understand, at least for me, than the functional version. So Sophia has a number of features that we will go through a little bit in detail. So first of all, it's a functional language in the ML family, so similar to OCaml, or even more so to the language Reason. But it also has significant white space, so you don't have to use blocks, curly brackets or semicolons to to show the block structure of a program or the scoping. It's strongly typed and it has a restricted mutable state. We will look a little bit on what that means in the examples that's coming. And it supports algebraic data types and pattern matching, so we'll see what that means soon. Also, Sophia has built-in support for the æternity features like oracles and names and so on. So let's look at some examples of Sophia code. Here we have a simple storage contract that handles state. So Sophia contracts start with the keyword contract and then the name of the contract. And then everything that is indented here is part of that contract. So first we declare the type state. So this is a keyword that is defined to actually handle the state that will be stored on the blockchain for that contract. So this state will be a map with a data and integer, or a record actually, with field data and an integer. The function init is a special function that is automatically called when you create a contract. So when the contract is first created on the chain, the init function is called, and in this case it takes an argument, and the init function is supposed to always return the type state, which in this case has to be a record with the field data. So we initialize the data to the argument number, and then we have the start of this simple storage stored on the chain. Then we can call the get function to read the state of the data, and the set function, which calls the built-in function put, that updates the state with a new value for data, which is the argument number in this case. So this is the basis of contracts. You have types and functions, and you have special type state, a special init function, and then general functions that you can call that can either just read a value or actually update value in the state. Sophia also supports calling other contracts, and when you call another contract, you have optionally named arguments, gas and value, and gas limits the amount of gas that the contract they call may use, and value is the number of tokens that you want to transfer from this contract to the contract you're calling, and both of these are in atto-eons, or 10 to the power of minus 18 eons, which is the basic token value that is used for fees and gas prices and so on in the æternity chain. So here we have another contract called ink server that has a function ink that takes an integer and gives back an integer. So in this case, this is only an abstract declaration of this contract, so that we may use it in the real contract that we're defining right now. So in the contract main, we can have also a function ink, which takes an ink server as an argument. So this will be an address to a contract on the chain, and that contract should have the same type signature as the ink server contract that we're declaring here. That is, it should have a function called ink that takes an integer and gives back an integer. What it does we don't really know from the code here. From the name we can guess that it will actually increment some state with the integer that we give it, and perhaps return the incremented state value. Our new function inc here takes the x as an argument, and then when it calls this inc, it actually transfers 10 tokens also with the optional argument value, and then the argument x that will be used to increment the value. So the inc server might charge a fee for keeping this this state to be incremented, for example, and it might check that it gets at least 10 tokens in order to increment something. As a very simple example. So this is how you do a remote call. You use the name of the contract that you want to call and the function you want to call with the dot in between them, and then the arguments to that function. For built-ins, it looks basically the same. So there's a number of contracts that emulates the transactions that you can do with first-class objects in Eternity, such as oracles. So, for example, there's a query function in the Oracle contract that takes a number of arguments. So you can create a new function called createQuery, which takes an Oracle ID, a query type, and a fee, and some time to live for this query. And you may check that you actually have enough tokens transferred in this call to transfer to the query fee to the Oracle. And the syntax for calling a built-in is the same as calling another contract, but you just don't have to define what Oracle is. The compiler knows that Oracle exists and has a function query that takes these arguments. Sophia also has variant types, so you can define your own types. Like, for example, here we define our own data type complex question that can either be to be or not to be. So this way you can define a data type that can take on 2 different values or a number of different values. They can also be parameterized, so they can take some types or a number of types actually to each constructor of the type. There's a built-in type that's called option. It has 2 values, one none and then some of some type. So we can do pattern matching on this. And so here we have a function has answer that takes an Oracle ID and a query ID, and it calls the get answer built-in function of the Oracle contract, and switch on the result of this, which will be an option. So if it's none, then it's false, there was no answer, and if it's some answer, then it's true, there was an answer to this question. So we can put this together, variant types and pattern matching. So we can construct a data type tree, which has 2 constructors, node and empty. And empty is just empty, and node takes an integer, which is a key, and a string, which is a value. So we can get a key value store out of this. And then it has 2 leaves, left subtree and a right subtree that are of the type tree. And then we can declare a function find that takes a key of type integer and a tree of type tree, and then we switch on a tree, and if it's empty, then we return none, we didn't find the key. Or if it's a node and the number that's stored in this node, the key in this node is equal to the key that we're looking for, then we return the value here, the string, which is an address. We return it as an option some address. And otherwise, if key is less than number, we search in the left subtree by calling find key on T1, which was the left subtree of this node. And if key is larger than number, the only case left, we look into the right subtree T2 to find the key. So if you want to learn Sophia, you should know that functional programming is a lot of fun, and there are many introductions to functional programming online. Just Google gentle introduction to functional programming and you will find many nice introductions. But if you already know what functional programming is, I think you will love Sophia and the ability to do functional programming on a blockchain. You can also find the definition of the Sophia language here, which looks like this. It's a very terse definition of exactly what's in the language. So it's not the easiest way to learn the language, but it's a good reference guide when you have started learning the language a bit. You can also look at examples that are used by the implementation to test the contract. So some of these examples are maybe a bit strange because they're trying to test different aspects of the compiler and the implementation of the language and the virtual machine. So they might not be so interesting, but some other ones you can actually see how they work in the and get some idea of how Sophia looks. So that's it, and I think we're going to take some questions now. So thank you for listening so far. Yes, also Eternity is all open source and you can find it on GitHub, including the